The content describes the question of how to prove Pythagoras' theorem. You can find this article written in this blog of mine. The link is www.mohanmecap.com/the-content-describes-the-how-to-prove-Pythagoras-theorem/. If you want to write articles, then you can go to this above-mentioned article. Now the article begins. To prove the Pythagorean theorem, we can use various geometric and algebraic methods. One of the most famous and widely used proofs is the geometric proof attributed to Euclid. In this proof, we start with a right-angled triangle with sides labeled as A, B, and C, where C is the hypotenuse, the side opposite the right angle. We want to show that the sum of the squares of the lengths of the two shorter sides, A and B, is equal to the square of the length of the hypotenuse, C. Euclid's proof begins by drawing three identical copies of the original right-angled triangle and arranging them to form a larger square. Each side of this square is equal to A plus B. Within this square, we can see that the area of the smaller square formed by side C is equal to the sum of the areas of the four right-angled triangles formed by sides A and B. Using the area formula for a square, we can express this relationship mathematically as A plus B superscript 2 equals A superscript 2 plus B superscript 2 plus A superscript 2 plus B superscript 2. Simplifying this equation, we have A superscript 2 plus 2 A plus B superscript 2 equals A superscript 2 plus B superscript 2 plus A superscript 2 plus B superscript 2. By cancelling out the common terms and rearranging, we get 2ab equals 2, A superscript 2 plus B superscript 2. Dividing both sides by 2, we obtain ab equals A superscript 2 plus B superscript 2. This equation shows that the area of the square formed by side C is equal to the sum of the areas of the squares formed by sides A and B. Therefore, we have proven that the sum of the squares of the lengths of the two shorter sides, A and B, is indeed equal to the square of the length of the hypotenuse, C. Euclid's geometric proof is just one among many methods used to prove the Pythagorean theorem. Other proofs include algebraic proofs, trigonometric proofs, and even proofs using calculus. However, Euclid's proof remains one of the most elegant and intuitive demonstrations of this fundamental geometric principle. I hope this expanded explanation helps clarify the process of proving the Pythagorean theorem. If you have any more questions, feel free to ask. To prove the Pythagorean theorem, we can use different methods, such as geometric or algebraic proofs. One popular geometric proof is the one involving squares. Here's a simplified explanation. Start with a right-angled triangle. Draw squares on each side of the triangle. The area of the largest square, the square of the hypotenuse, is equal to the sum of the areas of the two smaller squares, the squares of the other two sides. This relationship between the areas shows that the square of the hypotenuse is equal to the sum of the squares of the other two sides. This method visually demonstrates the Pythagorean theorem, providing mathematical evidence for its validity. To prove the theorem, you need to create squares around the triangle. Just paint the triangle and the squares as mentioned in the theorem. Then, calculate the areas of the squares. Here's how you can do it with a square box. Measure the sides of the square box. Square each measurement and add the results together. Take the square root of the sum. Measure the diagonal length across the square. You can follow the same steps with a rectangle. This process should only take about 5 minutes. Table of contents. Proof by rearrangement, geometry. Proof by algebra. Proof by rearrangement, geometry. The relationship between the sides of a right triangle can be fascinating. In this case, we have a right triangle with sides represented by the lengths AB, BC, and AC. By applying the Pythagorean theorem, we can find a connection between these sides. Starting with the equation AB superscript 2 plus BC superscript 2 equals AC superscript 2, which is known as the Pythagorean theorem, we can explore further. Let's delve into the reasoning behind this equation. When we square each side length of a right triangle and sum the squares of the two shorter sides AB and BC, we obtain the square of the hypotenuse AC. Now, moving on to the next step, let's consider the expression AB plus BC, superscript 2 equals AC superscript 2. It appears that we're squaring the sum of the two sides of the right triangle and equating it to the square of the hypotenuse. To understand this relationship, we can expand AB plus BC, superscript 2 using the concept of binomial expansion. By applying the FOIL method, first, outer, inner, last, we get AB superscript 2 plus BC superscript 2 plus 2AB BC. Notice that this result matches the original equation AB superscript 2 plus BC superscript 2 equals AC superscript 2, but with an additional term, 2AB BC. This additional term, 2AB BC, involves the product of the lengths AB and BC, multiplied by 2. It arises from the geometric interpretation of the cosine function, specifically the relationship cos AB, BC equals 0. When two sides of a right triangle are perpendicular, as is the case in a right triangle, the angle between them is 90 degrees, and the cosine of that angle is 0. By substituting cos AB, BC equals 0 into our equation, we eliminate the theorem 2AB, BC, leaving us with AB superscript 2 plus BC superscript 2 equals AC superscript 2. This simplification is useful when dealing with right triangles, because it allows us to establish the connection between the squares of the sides. Now, let's shift our focus to the concept of squares within squares. Consider an outer square with side length, A plus B, where A and B represent the lengths of the two sides of a right triangle, and an inner square with side length C. In this scenario, the corners of the inner square touch the sides of the outer square. By examining the areas, we can derive an interesting relationship. The area of the outer square is A plus B superscript 2, which can also be expanded as A superscript 2 plus 2AB plus B superscript 2. On the other hand, the area of the inner square is C superscript 2. Interestingly, the area of the outer square is equal to the sum of the area of the inner square and 4 times the area of the right triangle, which can be calculated as 4AB/2 or simply 2AB. Therefore, we have the equation, A plus B superscript 2 equals C superscript 2 plus 4AB/2. By simplifying further, we can express this equation as A superscript 2 plus 2AB plus B superscript 2 equals C superscript 2 plus 2AB. Notice that the left-hand side of this equation corresponds to our initial equation AB superscript 2 plus BC superscript 2 equals AC superscript 2, further reinforcing the relationship between the sides of a right triangle. In conclusion, the equation A superscript 2 plus B superscript 2 equals C superscript 2 represents a fundamental property of right triangles known as the Pythagorean theorem. It reveals a connection between the squares of the lengths of the sides and is valid for any right triangle. Additionally, the concept of squares within squares helps us establish a relationship between the areas of squares formed by the sides of the right triangle and the outer square enclosing them. I hope this elaboration provides a comprehensive understanding of the topic. If you have any further questions or require clarification, feel free to ask. I apologize for the confusion, but it seems that there may have been a misunderstanding. The previous response you received was the reply to your original question about using Pythagoras to calculate the horizontal length of a flat screen with a 16:9 aspect ratio. The explanation provided was meant to clarify that by using the Pythagorean theorem, you can determine the relationship between the diagonal length and the horizontal and vertical lengths. To elaborate further, the Pythagorean theorem states that in a right-angled triangle, the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the other two sides. In the context of your question, we can consider the diagonal length of the flat screen as the hypotenuse. When you multiplied the diagonal length by the ratio of 16:9, you essentially created a right-angled triangle where the horizontal length is one of the legs, and the vertical length is the other leg. By rearranging the equation derived from the Pythagorean theorem, which is a superscript 2 plus b superscript 2 equals c superscript 2, where a and b are the lengths of the legs and c is the length of the hypotenuse, you can solve for the horizontal and vertical lengths of the flat screen. By using the constant value of the diagonal length, copyright and the ratio of 16:9, you were able to maintain consistency in the ratio when calculating the horizontal and vertical lengths. This method you employed is indeed a basic application of high school mathematics and a practical way to calculate the dimensions of a flat screen using the Pythagorean theorem. I hope this explanation provides you with a clearer understanding. If you have any further questions or need additional assistance, please let me know. Proof by algebra. Consider a right-angled triangle increment ABC where angle A measures 90 degrees. To prove the Pythagorean theorem, we need to show that the square of the length of the hypotenuse BC is equal to the sum of the squares of the other two sides AB and AC. First, let's draw a perpendicular line segment AD from vertex A to the base BC. Notice that this creates two smaller right-angled triangles within the larger triangle, increment ABD and increment ACD. The similarity of triangles increment ABD and increment ABC, denoted as increment ABD tilde operator increment ABC, can be established using the angle AA similarity criterion. We observe that angle ABD is equal to angle ABC because they are both right angles. Additionally, angle ADB is equal to angle BAC as they are alternate angles formed by the transversal line AD. Therefore, we can conclude that increment ABD tilde operator increment ABC. Using the AA similarity and the corresponding proportional sides, we know that AB/BD equals BC/AB. Multiplying both sides of this equation by BD, we get AB superscript 2 equals BC asterisk BD, which will denote as equation I. Similarly, we can establish the similarity of triangles increment ACD and increment ABC, denoted as increment ACD tilde operator increment ABC. By applying the same reasoning as above, we find that AC/CD equals BC/AC. Multiplying both sides of this equation by CD, we have AC superscript 2 equals BC asterisk CD, which we'll denote as equation 2. Now, let's add equations I and 2 together. BC asterisk BD plus BC asterisk CD equals AB superscript 2 plus AC superscript 2. Factoring out BC from the left-hand side of the equation, we get BC asterisk BD plus CD equals AB superscript 2 plus AC superscript 2. Since BD plus CD is equal to the length of the base BC, we can simplify the equation to BC asterisk BC equals AB superscript 2 plus AC superscript 2. Therefore, we have proven that BC superscript 2 equals AB superscript 2 plus AC superscript 2, which is the Pythagorean theorem. Thus, in a right-angled triangle where angle A measures 90 degrees, the square of the length of the hypotenuse BC is equal to the sum of the squares of the other two sides AB and AC. Thanks, please see entire video and like it and subscribe it and then can share to ours near and dear ones. Thanking you in anticipation.